In this lesson, we're going to look at linear functions. I want you to consider matching each of the scenarios with a graph below that relates distance from home to the amount of time that has passed. See if you can take these three scenarios and match each one of them to one of the graphs below. Pause this video to take a moment to match the graphs. So in the first one, a student drives towards school at a constant rate. After a while, his favorite song plays on the radio, and he drives the rest of the way at a faster constant rate. So he's moving farther away from his home. For this scenario, the matching graph is B. We start at home. He's driving towards school away from home at a constant rate. And then his favorite song comes on the radio, and he wants to go faster. For the second one, a commuter is driving to work at a constant rate. The commuter notices a police car in the right lane and slows down so that she can drive at a slower constant rate. After a while, the police car takes an exit ramp, and the commuter quickly resumes driving at the original constant rate. This matches with graph A. The commuter's driving, she slows down, and then she goes back to her original speed. And so the last one would go with C, but let's see how it makes sense. A student drives towards school at a constant rate. After a while, he gets a flat tire, so he's stuck. Time is passing, but no distance is changing. When we're looking at these graphs, time is passing, distance increases as we go up. So he drives along, he's getting a flat tire, so he's stuck on the side of the road for a while, and then he's driving towards school at a faster constant rate to make up for lost time. Notice the incline, I'm going to avoid using a special word right now, the incline of these two pieces in our graph 3. So I'm looking at the steepness of this part and the steepness of that part. The second part is much steeper than the first, and that's indicating that he's driving faster to make up for that lost time. Try to draw one of these graphs for this next scenario. A student drives towards school at a constant rate. After a while, the student realizes they left their book at home. They turn around and head home at a faster constant rate in hopes of still getting to class on time. After getting her book, she drives towards school at an even faster constant rate. So we have our distance and time. Starting at home, she's driving towards school at a constant rate. Oh no, we forgot our math book. We've got to turn around and go home, so we're going to go back home pretty fast. The distance from home is now at 0 because she's back at home. And then driving towards school at an even faster constant rate, we need a steeper line going away from home again. Anything similar to that graph is good. These are estimates on the scenarios that are happening. And really, what I want you to pull from all of these different graphs is this idea of steepness, or in our class, we're going to call that slope. The slope of a line through two distinct points. Here we have a line, we have two distinct points, and we can calculate it as change in y divided by change in x. Change is represented by the Greek symbol delta, and delta looks like a triangle. Sometimes this is called rise over run, and you've likely seen this formula before for slope. We really want to find the distance here in the y's divided by the distance here in the x's. It actually does not matter which point you make come first, as long as the ordered pairs are lined up in the formula, the y value on top of its corresponding x value. More information that likely is a review, but it's a good refresher before we talk about the slope more. Y equals mx plus b is our linear equation. And if we take that y and turn it into f of x, we have a linear function. And m is known as our slope, and b is our y-intercept, where that line is going to cross the y-axis. A few examples here, and I'll make one small correction. The one below the A should be a C and not a B. Sorry for that. Here, find the slope of the line passing through each pair of points graph them on the grid provided, and label the rise and the run. So I'll start with the first one, and we'll plot the ordered pairs, and then calculate the slope and label the rise and the run. So we'll start out with -3, -1, and as a reminder, x comes first, y comes second, and we're going to use the x-axis, which is the horizontal, and the y-axis, which is the vertical. And these ordered pairs are just addresses for the points. So -3 on the x-axis, and -1 means we go down 1. So here's my -3, -1. You see the -3 on the x-axis and the -1 on the y-axis. That gives me that point. And then for 2, 4, I always start in the origin. We always start in the middle, where the two axes cross. And then I go to 2 and up to 4, and I get my other ordered pair, my other point. I can draw a line connecting them. If I extend it, I make a true linear graph. With this graph, I want to make a triangle. Create a triangle from those ordered pairs. My rise, 1, 2, 3, 4, 5, and my run, 1, 2, 3, 4, 5, help me determine the slope, the steepness of this line. So if we use the ordered pairs to calculate the slope, I'll use the second one first, 4, so 2, 4, and there's always subtraction. I'm going to use parentheses to help me with my negatives, because that second ordered pair has a lot of negatives. -1 on top, because that is my y value, -3 on the bottom. And now when I have these two negatives together like this, 4 minus -1, that's 4 plus 1, 2 minus -3, that's 2 plus 3, 5 over 5, which gives us a slope of 1. I do want you to notice the rise and the run here match up with our formula. I also want to point out that the slope is positive. We get a +1 answer. And that's because if I'm a person and I start on the left and move to the right, I'm moving in the positive x direction. A positive slope means I move uphill. So I'm moving in the positive x direction, but if I walk on that line, I'm walking uphill. My height is increasing. Let's take a look at B, the one on the right. Plot these points and see if you can do this one on your own, and then resume and we'll talk about it. Did you get -7/5 for B? That's right. If you didn't, see if you can find your mistake. I wrote the slope out in 3 different ways here to illustrate that that negative sign can end up in essentially any place on our fraction, whether it's in the denominator, on the whole fraction, or in the numerator. All of these mean the same thing. Also, if I'm a person on this line moving in the positive x direction from left to right, notice that my person is now walking downhill. My elevation is decreasing, so I have a negative slope. Try C and D and see what you get, and then we'll discuss. In here, in part C, if I try to move in the positive x direction and I'm walking along this line, I'm not increasing or decreasing in elevation. I'm staying flat. So this slope is 0. And we can see that in our graph, that we're not going up or down. We're just staying flat. For D, if I try to calculate my slope for D, I get 3 divided by 0. Dividing by 0 is not allowed. This is undefined. And in this one, if I'm trying to walk along this line, I'm actually on a cliff, so our slope is undefined.